Okay, so maybe we can get started. Today we will talk about encoder decoder. So this is a very important structure. So a lot of things we will talk about in the future. We will have this architecture. And autoencoder is something which is part of a special encoder decoder, so we will go there. But first, I mean, for encoder decoder, almost anything now in prediction, in generation can be considered encoder decoders. So encoder basically is used for representation. Decoder can be used using the representation for both prediction and generation. So basically, this is a kind of a universal architecture and which has been used. So this is an important concept, and we will give some examples, and then we will move to the autoencoder. And next time we will talk specifically about variation autoencoder. So basically, okay. So let's look at the topics. Yeah, I mean, encoder decoder is just a concept. So we will try to use some examples to see these concepts. I mean, the example doesn't have to have the state-of-art architecture, but it's just for illustration. Then we'll talk about autoencoder. That is for representation learning, unsupervised representation learning. Denoising autoencoder and show how to use that for generation. Then next, so this one will pave the way for variation autoencoder, which will be the topic next time. Okay, so encoder decoder is basically like this, right? So this is architecture. You want to either using X, which is let's say look at the prediction now, right? X using prediction, for example, is an image, anything, audio, whatever it is, and then you go through the encoder to be a small representation Z. That Z usually is a vector. It doesn't have to be. There are variations of the theme, but generally you can say, oh, it's a vector. Vector, if you look at this shape, vector usually have a small dimension, smaller dimension than the original object. The reason is you want to compress the information of the original objects through the encoder, and then you use the encoder to do the decoding. So decoding gets you either the prediction or generation. So both on the right-hand side of this. We will talk about the generation, I mean, for the purpose of generation soon. Yeah, so you can call it embedding, or you can call it sometimes called code, representation. They are all pretty much the same thing. For yeah, it's as I mentioned, it's a small dimension. What if it's a large dimension, right? If a large dimension, one thing, especially when you look at the autoencoder, you just learn identity map, which is not too interesting. You want to learn representation so that similar objects will be similar. They have some concepts in the smaller dimension. The compression, right? So Y can be any objects, right? You can do either, again, it can be prediction, can be generation. So we will look at the examples of these. Right, so basically, this is a summary I mentioned already. So encoder is for representation learning, right? So it's just for representation. It's MAC input for latent representation Z. And the idea is to keep the useful information that is useful for whatever the downstream task. Downstream times, so when you plug in a decoder, then you can use the decoder for, again, for either prediction or for generation. Decoder for generation, right? So basically, it maps Z to output object Y. If a Y is a label, then it's a prediction, could be, right? So if Y is a complex object, you can do a generation. And if you want to do generation, right? So you can you need only the decoder side. You can starting with the Z. For example, a typical setting is you hope you map the representation from the original X to Z such that Z is like a Gaussian. It's a vector, Gaussian vector, right? So if a Gaussian vector, you just randomly sample Z and then goes to the output object. So that's how generation is done. Especially we'll handle that. How do you do that in the next lecture? So if you think about the Z, right? So you can say it's a single vector. It's an embedding of your X. It could be a structure sometimes, sequence of vectors, text tokens usually. This is the one we do the LLM with images, right? If you say how the large language model understand images, they do something like this. You map that to tokens. This can be done. We will talk about that later. I think in the part 3, when we talk the first lecture there, we'll talk about the multimodal, which will do that. Or you have basically you have a feature maps and so on. But you can think just for simplicity, you just think as a single vector, which certainly will be the case we will study here, at least for a while. So encoder makes good representation. Decoder uses Z to generate. So that's the story. That's basically. Turns out you can try to use this to rethink a little bit about what we are talking about earlier when we do the prediction, classification, and so on, like image classification and so on, right? So let's look at the image classification. What is encoder? What is decoder, right? So X is image. In the image, Y is a label, right? So it's a cat, dog, horse, and so on. Z is essentially some encoding of the image by the encoder. It's a representation of the image. That's generally what your CNN is doing. CNN, once your output of the CNN will be some kind of flattening. Once that has done, it's like a representation. Basically, CNN maps image to vector. So that's what it does. Decoder, you use fully connecting neural nets, right? In the end, if you recall the CNNs, when the classification, it takes flattened image vector on the top level. Then you map that to the logits of the class label. So that's basically the decoder, what the decoder is doing. Typically, for the case of generating this kind of discrete data, we usually the decoder always map to the logits, right? We talk about that. We just reemphasize here rather than the probability, right? So this because again, just reemphasize this one. You go through the softmax becomes your probability, then goes to negative log, become negative log likelihood. Together, this is cross one entropy, right? Called. So basically, yeah, you work with the logits. You don't work with the probability. Okay. So that's the typical setting, and here is an encoder, which we probably have seen before. It just just illustrate what is the outcome of encoder. So you can write that as an encoder-decoder architecture, just using this is mainly conceptual, right? So you just so that you map these to other things. The thing about the encoder is once you do encoder, it's a representation of your image. You can be used for other things. Not only just, for example, if you use train this encoder on ImageNet, right, for the ImageNet classification, you can use this as a representation to do other classification or other tasks of your image. So this is a simple CNN, which in the end, if you look at that in the end, it's basically mapping, right? You can call this one is a mapping, but because we want to output to a certain dimension, we just say, okay, I want to fix whatever dimension you want. For that one, you need additional linear mapping from whatever the image CNN gives you in the end of your network to whatever your embedding dimension. So this one is your embedding dimension of Z, right? So basically, basically this one gets you a vector. If you look at the code, in the end, it gets you a vector. That vector is of a dimension Z. Okay. Decoder, then you can say, okay, I will take this vector, map to the logits, right? So basically, this one is two-layer neural nets, right? You have a linear. You first goes to the intermediate, and then you goes to intermediate. You goes to ReLU, then goes to the 10. 10 is it's an MNIST CFAR, right? So those are the class labels. So this basically get you what is a decoder. So if you separate that, the main thing is you can this decoder for the classification is separated from the representation. Once you take the representation from encoder, you can do other things with that. So that's the conceptual separation about these two. Now let's look at the image classifier. In this case, you say, first I will look at the image. I will represent it as a vector. So, so basically here Z is a representation of this image, starting with the image, doing a representation learning using recounter, then this becomes a vector, right? Given the vector, I will say just the standard two-layer neural nets will be the decoder, and then you just do the classification. Depending on this vector. So that's basically the conceptual separation about encoding, decoding for image classification. Using this idea, you can do whatever you want. You can do a lot of other things, including generation and so on, right? So for example, this is a little bit more complex task than image classification. So this is an image. Then you want to say captioning means you want to have a natural language description. This particular example is coming from the Microsoft Cocoa, which is a very common data set for this kind of captioning, image understanding, detection, captioning, and so on. So essentially, you just want to describe using natural language, describe what this scene is talking about. So this is a little bit harder problem than classification, right? Why? I mean, because it gives more information, right? You also need a natural language, and so on. So instead of just keep labels. So labels are just very simple information. This one can have multiple objects, can talk about their relation, what they are doing, and so on. So this is a standard task in image. Just try to describe image given this, right? So when we do that, what we can do? Again, nowadays people probably using multimodal LLM to work with this kind of tasks, which does pretty well for this particular kind of tasks. But you can in either case you do have an encoder decoder. So we will just try to, from understanding, we will look at the architecture, what we are looking at, right? So, so encoder is you started with X, right? You do an encoding vector representation of an image. Again, we just do simple things here. Here, because we are just for illustration, not really say we want to get the best, whatever the image captioning model here. So we just do simple things, X to encoder, right? So, and then Y is a text description, right? We have seen the text generation using LSTM, right? So basically, then we can do that. So here is a simple design just for illustration. CNN to map image to a vector Z, right? So this one maps to Z. Decoder LSTM maps Z to text Y, right? So represented the token sequence by using Z as a conditioning. So that's basically the simple design. So if you are doing that, then you are separating this problem into the encoder decoder. Okay, and then once you have separated this into the encoder decoder, then basically it's a, you just need to say what encoder I should know, what's the decoder, right? Also how they interact. This one is simple design because we haven't talked about attention and so on. Nowadays, most people when we're doing these more similar to the like transformer architecture using cross attention and so on. Maybe we'll talk about that later, right? When we talk about transformer or multimodal and so on. But here, just it's just for illustration. So. So LSTM, right? So essentially, each token, we know it goes to embedding. It becomes a vector for each token here. You generate token, usually you always next token prediction, right? From 0 to 1, token 1 to token 2, right? So this we know, and this we talked about last time. And then here just say, oh, the simple design is just concatenate all these vector to each position, then to get this. Okay, this is just for illustration. So this is the one design you can do the conditioning about in your encoder and then doing that. As I mentioned, there's a lot of more recent one we use attention to do cross attention and so on to do this. But anyway, so this is one design. And here is the CN encoder. So this one uses a pre-trained network. Basically, you could do that, right? So pre-trained ResNet 18 is you can pre-train on the ImageNet. So it's already there, right? So essentially, you just work with just take whatever. So that's another thing about separating encoder decoder, right? You can always using something like a pre-trained network, and then you fix that where you alleviate a little bit, which we will talk a little bit about this here. If you look at this code, right? Let's say I'm doing this training. Now, I'm just showing you, this is, let's say you have a pre-trained model, right? This ResNet 18. When you read this forward, here is no gradient, which basically says when I do this network, this is frozen. We don't need to track gradients of these basically, and then the other one you are doing whatever feature. So when you have an encoder decoder, you're using some kind of pre-trained. You can always frozen some of the models or part of the models. You just leave some other models to be doable, right? Instead of just trying to work with all the models, basically. You can freezing some of the weights. Decoder is a embedding vector. So this one eventually gets you embedding. So basically, this is embedding size. This is a dimension of z, basically in our notation, right? So basically, yeah. So here is essentially just get you back the features and so on. For the decoder, for the LSTM, you basically take that. Using our design, as I mentioned, we have a specific design. This design is just for illustration. Basically, it's concatenate your, let's see, your embedding. Where I just want to take a look at here. This forward is basically here. Yeah, here is your embedding and basically features, right? So essentially you concatenate. Yeah, this one just say you are concatenate. Just showing earlier that one. This is just one specific design. There's nothing particular about that. Just for the illustration. So you can write this kind of code and so on, and then you are doing the LSTM basically. So essentially you replace the inputs to your LSTM by using these guys, basically by using the additional ones. Yeah, then you then basically you are doing. This particular is more for the training. Yeah, for the training purpose. Yeah. So you do that the whole sequence. Okay. Anyway, so yeah, so this one basically implementing the two ones, and one thing is when you do the encoder decoder, if you are care more about the generation, if you have good representation, you don't need to change representation or fine tune a little bit about representation. So this is a constant theme when we do later on, even for the multimodal LLMs and so on. So that's usually you frozen quite a bit of the representation. Just move a little bit, which you want to train. So this is yeah. So let's look at this example, so-called sequence to sequence. This is a well-known paper. Again, it's a conceptual paper. The paper itself doesn't really has a lot of new things there. It's just conceptually you say you can generate a sequence out of another sequence as a way of doing, for example, translation, right, or other things, or question answering. And this idea is somewhat like the prompt idea. Nowadays, everybody's familiar with. You probably use that when you interact with GPT, right? So prompt is a sequence, and then answer is the other sequence. At that time, certainly, it's about 10 years ago, a little bit more than 10 years ago, right? So it's a prompt is not something which appeared yet, but a sequence sequence is a kind of precursor of that. Essentially, it embedded this idea to say, oh, I just using the, more or less, you can say, oh, I just using the decoding, right? Just generating sequence continuously in some way that it seems to work well. And for example, for machine translation. So that's one task a lot of the earlier NLP works are doing. So encoder is basically what you do is let's run LSTM on because at that time there's no transformer yet, so we will do LSTM. So I have a black hat, right? So this is an English sentence. Then essentially we just encode that sentence into a vector. So what that is. This one typical for the, usually this Z will be just LSTM states. But it could be other things, but for now, let's say just LSTM states. LS encoder, you get eventually it always hidden states get propagated. If you recall the generation, also our homework has our homework, I think the next homework will have this, but basically you carry on if you look at the code provided, you carry on your hidden states one token at a time when you do the generation or the earlier. So essentially, this one will be the hidden states of your LSTM. And it goes to the decoder, right? Decoder is continue. Essentially, it's all things, if you choose together, it's just continuing doing LSTM using the encoder to encode this English sentence. And the representation itself is just the state, the hidden state of your LSTM after you are reading this sentence, the LSTM. And then you continue to say output Spanish and so on. So this is the sequence to sequence framework. And yeah, and it's as I said, it's not anything specifically technically to say what's new there. It just it's more conceptual, right? So you treat one thing as encoder, treat one decoder, or alternatively, you can say you're treating one as a prompt. You are treating the other one as your answer, right? Yeah, basically hidden states, right? So essentially, and the decoder receives Z and the initial context, then you just continue decoding. So that's basically what you can do. Yeah, I believe this one, I have to double check, but I think this one is 10 years best paper, probably for NeurIPS that year, if I'm correct. But certainly it's well cited because of, again, because it's a precursor. If you think about precursor of prompts, right? Prompts everybody use now. It's just not at that time. Basically, it demonstrates successful of this paradigm. And this is very general. Now we also know it's very general because the prompt, you can ask anything, you can do anything, which certainly make it very general. But again, at that time, it's not entirely, no, this is methods, or this is a paradigm one can use. So, yeah, so basically this is that's it. So basically, so this again, you are treating that as encoder decoder. What is encoder output is just the last, you just continue doing LSTM, but because of at any state, LSTM is recurrent. So at any state, the state itself can be considered as a representation, can be considered the encoder output. So yeah, so basically just keeping running LSTM and treat as prompt, right? Continue to generate responses, and then you are done, right? So here is the encoder, right? So essentially, if you look at the outside, and basically this go, basically you just goes whatever the outputs. We know the LSTM has this hidden and the cell, which we talk about. The detail doesn't matter much, but essentially it will each time it will keep track of cell hidden, right? So and then they will generate outputs. Outputs generated from hidden, right? So and then basically, as long as you keep these two, you can just keep continue decoding with LSTM. It take this guy as input each time and generate the next one as output when you do a token level, token by token coding. So this is basically a pretty simple encoder decoder architecture. You basically are encoding by using this this idea, and the decoder you just continue, right? So basically, you're starting with this hidden cell, right? And then each time you're looking at one token, you're generating a next token, basically. So you're taking the hidden cell and you're generating next the hidden cell and so on. So basically, you just iterate, right? So yeah, so basically you just this is one by one generation. So decoder usually you are doing that for generation, and the encoder using for representation. So that's very typical. And if we turn that into transformer, right? If you think about turning that into transformer, then it's that's a modern architecture, basically. I mean, that's no much difference. Another thing is we separate the encoder decoder for conceptual. There in the transformer, there's interesting things which we will talk about earlier. You could also another thing is if you just run from left to right, let's say for the LSTM, right? You can say encoder decoder they don't have much differentiation. And they all actually, if we call, what do they correspond to in transformer? Later on, we call decoder only transformer, which was basically the LLMs, the modern LLMs. And then essentially, yeah, this one is pretty much has a setup. How do you want to run the modern LLMs using these, but separating for the encode and the decode. Okay, so any questions so far? Okay, so no questions. I'm continuing. Yeah, one thing you can think about that. The other thing you can think about that is here it's treated at pretty much the same, just running as LSTM from left to right, because it will produce hidden, right? Alternatively, you can think I can make it asymmetry, right? Just like image classification and so on. We, in addition, we're putting additional efforts or using a different encoder and decoder, right? So then your hidden state cell doesn't match. then in that case, you say you're using a smaller decoder and a larger encoder. Just for example, I mean, then you have to map that back, right? Just like what we did with ResNet, right? You say, oh, I have to match that hidden cell into the same representation which is suitable for decoder and to use, and then we will continue from there. So it could be asymmetric instead of a symmetric when you have an encoder decoder. But one thing for this kind of a sequence task, which is very special because sequence is like uniform, it's kind of continuation, just keep writing. So they can be, encoder, decoder can be the same. Yeah, this is very special for the sequence. Image to text, yeah, you cannot immediately say that, right? It cannot possibly be the same, right? So you can think, but the sequence to sim, they are uniform, and then they are pretty much can be the same. Yeah, here basically is what you do with so sequence to sequence model. Just a very simple illustration again about what we are doing. So sequence to sequence. Sequence to sequence. What we are looking at is first we are doing encoder, right? So this is your input is basically source, right? I mean, because we are really thinking about machine translation, so you have a source target. If you're now say more familiar with the prompts and response, right? You can say this is a prompt, this is response. Okay. Source target. So your encoder try to take the source, right? And basically all it does is take the source. Then it's output your hidden cells, right? And for the decoder, it just keeps running for the target length. You just take your hidden cells. You go through one at a time, and then you generate outputs basically. Your generate outputs, then you carry on these hidden cells. You just recurrently carry on hidden cells and also generate output at the same time. So output usually, again, for this task, almost for all our tasks, it's a logits, right? Basically logits of each token position. Is each output. Yeah, that's about it. So so I hope that's not too complicated. This, as I said, there's no technical innovation or differences. It's more conceptual. Just thinking that as when you're decoding sequence as encoding decoding. So sequence to sequence model. So that's one of the encoder decoder example. Now we are done, at least with the encoder decoder. So what we want to do now is going to specialize the encoder decoder, right? Called the autoencoder. So autoencoder, what does that mean? So essentially, it's like a representation learning using unsupervised data. So I just give you X without Y, right? If I do, let's say if I talked about ResNet 18 as an encoder before, how it's trained. Usually, ResNet was trained on ImageNet. It could be other data, but let's say ImageNet. ImageNet has labeled data. You have images. You also have something like label. So use image to learn label. Those are supervised learning, right? So and then you using that, you gain some information about the representation of image because you are text representations, and those representations ResNet will be output. So those are learned. It's a supervised representation learning. Now let's say I don't give you a label, right? I give you just the ImageNet. I'll remove all the labels. I just give you the images. Can you still do representation learning? So this is a topic we will do for 3 classes. This class, right, we're starting that. Next class is VAE. Then we will talk about contractive learning. So those are the key, especially the next 2 classes were the key ways, the more ways which you see of doing that. But the autoencoder is a little bit more ancient version of. I'm sure it actually appeared probably quite early, so I don't know exactly how early it is. It has to be like maybe even in the 80s or 90s. Yeah, I actually don't know because this one comes, people just talk about that as natural. So I don't know the original source, but certainly it's well known even before when people talk about the neural net representation learning. Let's say just give an image X, right? So you go through encoder. This one has to be a lower dimension. This one say image is, let's say is 28 by 28. And this one say 16, 32, or 2, whatever. The size, you need to be much smaller in the dimension so that you have a compression effect. And hopefully what is compression is a similar images without knowing the label, but similar images get compressed together. Which means you using this smaller image can represent your original image, right? So basically, all the other information removed, you just need a smaller amount of information to represent your image. So encoder, this is this is sometimes called bottleneck. You're compressing. So encoder is certain neural nets which will allow you to do that. And the decoder is a neural nets, which allow you to get back from this one to the original image. But then because you have a compression, so X and X tilde probably not the same, right? In the typical case. Then you have a so-called reconstruction error to measure. Usually it's a mean squared error, but you can put other things. So reconstruction error to say how good my reconstruction is of my original source. So the idea is training encoder decoder simultaneously going through a bottleneck such that you have a smaller reconstruction error. Is it clear? Or? So basically, this is a key idea of autoencoder. Want to find the encoder decoder so that after this decompression, right? You have almost no loss of information. And this is measured by this reconstruction error. Right. So basically, this is, or distance or some agile metrics. Typically, actually, although we say distance, maybe I should remove so-called distance because usually we have a least squared error, just x minus x tilde squared mean squared error or squared loss, right? So it's a learning of vector representation z embedding of x. So that's the part. You can actually do two things. What's interesting, this one is, again, if you recall, I mentioned earlier, encoder is for representation, right? So once you have a z, you can use that for downstream tasks. That's one use. The other use is generation. Generation, we will talk more. We will show quickly today, but we'll talk more next time. Using z to generate another feature, another elements. So you generation is what we call generator. It's basically decoder. Decoder is giving you a representation, and then you coming out to be your original, right? So this is part is the generation. The other part is representation. So this is how it works, and we will see talk about examples, and talk about train. Autoencoder training. You have unsupervised thinking about the ImageNet without a label, right? So that's your data. Encoder network, you have a model parameter phi. Basically, it's neural nets. Decoder network, you have a model parameter theta, right? And this is your training. Basically, you go through the encoder. Usually it's a lower dimension. That's why you have a bottleneck. You always have a compression. No matter what you do, you have a compression, right? This is a decompression. So there has to be some information loss because of the bottleneck here, right? Z is a smaller dimension. This gives you Z. And then this guy is, the squared error. So that's basically what you are trying to minimize. encoder decoder. So this is a general framework to do auto encoder training. Okay, so now let's say what we do here. One connection is PCA. This is for the classical statistical or machine learning. First course in machine learning, they always talk about PCA. Essentially, it's a linear autoencoder. So PCA, what you can do is you are mapping a matrix to map this from larger dimension to smaller dimension. Let's say this is a D dimension. Z is M dimension. M is much smaller than Z. Maybe I will add a dimension here. Just say M is smaller than dimensional Z, right? So this one mapping is linear and linear out. So this one will give you something like a PCA, right? So basically, PCA is a special case, but the modern ways of doing autoencoder is not using linear, but using neural net. So this is just the strict generalization of PCA. So autoencoder is. Yeah, basically it can be used as nonlinear PCA. So it's basically a generalization. So you can always, if in your PyTorch code you just have a linear layer, then that's PCA. Okay. So let's move on. So let's look at this case, which we are looking at. So this is autoencoder reconstruction. So basically, I just train autoencoder. And this autoencoder, this is the original image, right? And here is a reconstructed image. And this is a difference. For this particular example, we have encoding the autoencoder the dimension of Z, which is the representation is 16. MNIST again is 28 by 28. It's a grayscaled, so it's a it's a larger dimension. Once you drop that, you can encoder dimension is 16, which gets you a compression, right? Once you compression, you can actually still reconstruct the image pretty well, because that's simple. It's just 0, 1, 2, and the div is this guy. Okay, so. But now let's look at my encoded dimension is smaller, right? So 16 is pretty, that clearly, you still get something here, the same image, right? When you train autoencoder, when you try to, I believe the code is given. So we didn't give the code for the earlier representation learning or encoder. Those are just for illustration. But the code for autoencoders, I think are provided. You can take a look. And basically, with a modified dimension, this is a smaller dimension. Certainly, you have more bottleneck effects, more compression, right? You can see that it's a little bit blurred. You cannot capture all the information. Even here, you're missing some information, right? This part probably is harder to represent. So here you don't see as sharp here, but reasonably close here. It's more smoothed out. It means you have a compression, right? More compression, and you have a more reconstruction error. So here is so basically, it just say you're tuning that. But it depends on your purpose, right? Your purpose is not necessarily always for generation. Your purpose may be for representation. Even you have a loose information, this may not be that important, this information. So this representation of a 2-dimension, you have a more compact information, might be more useful. So you cannot just say, I look at the reconstruction error to tell, because they have a different dimension. So this one can be considered as kind of a tuning parameter, which you have. Here the code, right? So code, actually we will talk a little bit about the decoder code. So the encoder code is just CN, which already we have talked about both of that and also in the homework. but we just quickly go over that. Just say, you know, this one is basically, you start with 28 by 28, you have a kernel size of 3, right? If you recall, this one is from 1 channel, input channel to 4 output channel. And the padding is 1 means you do not shrink your image, right? So just refresh everything. This is a ReLU, so that's typical. Max pool, now it shrinks the image, right? So basically max pool, if you have a kernel size of 2, strata equals 2, which 28 by 28 become 14 by 14. We are, instead of working with one of the one channel, you are working with 4 channel. Turns out, you know, if you think about that, these are the same dimension because you have a 4 channel, right? So you don't have information loss. You just have more of a representation here. Then you do another ReLU. You do I think you get here is another, you are increasing another from 4 to 8, another convolution. This by the way, this network is just arbitrary, so it doesn't really mean that this is such a great design, right? Just for illustration, right? So I mean, it does not have to be the best CN you can derive. But it is very typical, right? So you essentially, if you recall, we reduce the spatial resolution, we will increase the channel size. This is just refresh your memory. We are going through this so that you know how it's supposed to be done. And again, this is becomes by 2, right? It becomes 8 by 7 by 7. Then you increase the channel again. You reduce the spatial dimension again. So 7 by 7, you have to remove one of the pixel, become a 3 by 3, right? So 16 now channels, but 3 by 3. If this is the final, then your flattened distribution is a 16 by 3 by 3 vector, right? It's basically it's a 1 vector of size 16 by 3 by 3, right? And then you map that to the D dimension. This D in our earlier example is either 2 or 16, right? So basically then that's your representation of CN. Okay, so let's do a decoder. Decoder, we will talk a little bit more because decoder is you start with a Z dimension, which is whatever you get. Let's say 2 or 16, right? So think about that. Then first, what you do, right? You actually, I just try to reverse the CN. You don't have to be. Doesn't has to be symmetric to the encoder, but this one try to be invert your encoder in some way. So the design is somewhat symmetric to that, just for illustration. Again, this is for illustration, right? So this one, because recall that output before we are reducing the Z dimension, it's a 16 by 3 by 3. So first we will make it 16, enlarge this by linear, just to 16 by 16. This is not inverse of each other. It's only inverse in shape, right? If you think about it, it's always through the bottleneck. If a linear, linear from a high space like 16 by 3, go to low space about dimension, let's say 2, go back. It's like a PCA, right? So basically, you are compressing something. You only make the most prominent direction, not all the information. So it's not a inverse. It's more about approximate inverse in the sense of shape matching. Yeah. So you match the shape now. Now you have 16 by 3 by 3, right? You unflatten. Basically, this is your dimension. You are giving that back, your original dimension, right? So 16 by 3 by 3. Now let's make conversely, what you are seeing is doing the inverse of sometimes called the deconvolution or transpose the convolution. And this one again is for dimension matching. It's a transpose. It's not inverse. Doesn't say it's an inverse CN, right? Although it's called a deconvolution. It just say from a lower dimension, now you can make it a larger dimension. Convolution always larger dimension goes smaller when you do the stride, right? You make it smaller. I think there are 2 parameters, convolution, there are stride. there's a dilation. Dilation really is about the kernel, so we don't need to consider that. But stride, make it smaller. Here, stride, for the deconvolution, it's the inverse in terms of shape. For the stride, it's make it larger. So starting from 16x33, going deconvolution or transpose convolution, you first reduce your enlarger, you reduce, right? So your kernel from 16 to 8. Your kernel size is 2. Stride is 2, which really try to increase your spatial resolution by 2. And the outer padding, you're adding 1 dimension. So basically, this one somehow you are 3x3. By doing this, will be 6x6. And with an outer padding, it becomes 7x7. So basically here it's become 7x7. We'll talk a little bit about the more detail about the deconvolution or transpose convolution after these slides, just to give an introduction, proper introduction about that. But for now, let's just see the shape, right? You're starting from 16x33 to 8x77. And after that, you do a ReLU. You do another ReLU, just introduce nonlinearity. You do another transpose convolution to further enlarge, right? At this point, your convolution is you're keeping your channel size, and you are enlarging your spatial dimension by 2. So this one basically 7x7 to 14x14, essentially. Now what you have is about 8x14x14. You're doing another ReLU. You are doing convolution 8 to actually 14x14 here. You are doing ReLU. You are doing another 14 to 28, right? 28 after that you are yeah. I think this one is a 1 to 4, but the when you do the deconvolution, it's not exactly symmetry in the sense of it's 8 instead of 4. But nevertheless, you're just doing another convolution which make it 8 to 1. So in the end, what you have is 1 by 28 by 28. You have you make sure this one is a kind of your logits. You could keep it here, right? Or in the end you say, oh, I just want to image outputs. Then it's this transformation is typical. It makes it -1 to 1, right? So basically it just finalize, right? So then that's all. So basically, deconvolution, convolution, and all you say is when you do the CNN decoder, you want to CNN encoder, you're typically using convolution. Decoder, you use transpose the convolution, deconvolution, and so that you increase your spatial dimension. And strike there increase spatial dimension, while strike in the convolution reduces spatial dimension. Okay, so let's try to talk a little bit about that. So autoencoder is basically all it does is you have an encoder, right? Going through bottleneck of 2, and you image to this 2 dimension. Decoder is from this 2 dimension to the output image, and then you are done. So you just use a backprob. After this, you just use the backpropagation. You can compute whatever you have. So this is the code reconstruction error. Yeah, this is your loss function. Right? This is you can use sum, you can use mean, but basically mean is probably a little bit better because it's a large dimension. It's 28 by 28, right? So you mean make it the range is more manageable. So this is what it is. Okay, so now we have that. Let's talk a little bit about deconvolution, just to have a proper introduction, right? But we now know already. You look at the code as explain about the shape, you know what it does. But just quickly give convolution. It's a downsampling. It's typically used for the representation learning, right? You want to reduce the information. Representation, your tends to reduce the information. Generation tends to increase the information, just coming out from nothing, right? So you're thinking. So you have here is this is your kernel, and the size of this guy, right? And this guy typically is not larger than this, right? Smaller, you buy if you have a stride, strided convolution, stride is 2. This one is roughly half of this. So deconvolution is you can do reverse. If you say stride equal 2, right? So in the convolution, it reduced by h to h over half. Deconvolution stride equals 2, which increase the spatial dimension by using h equals half to full. So basically, that's yeah. Essentially, the mapping is in the shape, as I mentioned. It's not in the information. So basically, that's increases with the stride, decreases with stride, right? Transpose is not inverse of a convolution. You cannot inverse a compressed version, right? So it's more, oh, this is strange. Okay, it's learned upsampling that spatial this one probably should be larger than 1, right? So and you fix this symbol. But the stride is more than 1, then commonly use the decoders for image generation. So basically, this is why we are doing. Certainly nowadays people again everything more convert to the transformer, but still it's useful to know this. Okay, for the simpler version, C and both deconvolution. Okay, so yeah, stride larger than 1. So this one just increasing. We see that kernels 2, stride is 2, and so on. So let's just take a look at how it implements this one. Conv strike equals 2, right? Basically, you just moving kernel every two positions. You just make it smaller, right? So this one is like max pooling. People tend to use max pooling instead stride equal 2, but you could use stride. But reversely, what happens is these guys get packed, right? You're starting, this is starting. Before the convolution operation, you are padding out of 0, because you don't know this thing, right? So you just pad 0. And after that, you do a convolution, right? Kernel, let's say equal 2. Once you have this larger image, you can use a 2x2 convolution, and which smooths out this 0. So starting with that. So basically, that's kind of how you think about how that's implemented, right? Essentially, you first increase the spatial resolution, and then apply the same convolution method. For the convolution stride, your convolution that shrink, right? So basically, yeah. Convolution with stride S, map of starting from a high resolution feature of size h. You apply every S pixel, so basically reduce by spatial S, right? Basically, yeah, you reduce and the result spatial you decrease by a factor of S, right? So basically, stride S. Here, convolution with stride S, you are lower resolution. You insert zeros like these guys, and then you apply standard convolution after that. And basically, yeah, that's basically how it does that. But for our purpose, we all know what we all know is you just increase the spatial resolution. Okay, so I hope that's not too complicated, but basically, you just I think somehow you kind of remember if a stride, I mean, convolution reduce, transpose convolution increase, then that's all it's needed. But if you are interested, here is how that's kind of implemented, right? So basically. Okay, so let's now move on. So what we are looking at will be denoising autoencoder. Before that, I mean, this is the last topic we are doing here, and next time we'll go to the variational autoencoder. So this class, the good news is it doesn't have a lot of math. The next class really has quite some math. So I don't know how to reduce that, but again, so hopefully we at least give the all and formulas. You can understand the result of the calculation. You have to be good good at calculus in order to follow the derivation. It's not too complicated, but still, you need to refresh that. But here we don't have math. It's just a very simple math, or if there's math. X noise, C, and encoder. So why we want to do that, right? Usually, autoencoder, when you Z is a large. Let's think about the Z is a relatively large in this case, right? You learn alternative map. So essentially, you cannot always compress. That's not ideal. So to alleviate this problem, so what do, right? Basically, you add noise to X to make the job harder. It's like denoising. Denoising the things is you can never learn identity map. So that's the key part which is try to resolve, right? So that you hopefully learn better representation, because you can, if you can denoise your signal. Think about that, right? Noise is unstructured. Your signal, what X, is probably structured. If you say I add a noise to the image, your signal, then turns out my encoder decoder can denoise that. You have to learn some structure from that. Differentiate the noise and so basically that's the idea. So you add a noise here. The simplest, you could add a different kind of noise generation, right? So you have X noisy, but the simple way is just add a Gaussian for the image. Just say add a Gaussian noise here. Now you pass the decoder. I mean, the other thing, they're all the same. Basically, you pass encoder, pass. Again, what is trying to hope is you learn better representation, because you can differentiate noise from your representation, the signal, right? Also, you can never learn identity map, simply because you always denoising, right? You are guiding this one towards noise, the clean version, right? This one is guided through the clean. So and the simple version is just adding noise, right? This is a noise strength, will be a tuning parameter, sigma square. It's a Gaussian, where it's a spherical Gaussian with certain variations, sigma square, and then you add to the noise, and this one becomes your noisy. Once you have say, okay, if I have the ability to use this encoder decoder to get back my X, certainly we learn something. Learn better representation. So reconstruction error is again the same thing. I mean, it's a noisy. This noisy doesn't has to be this. This one is just a common way for our purpose, but you can imagine other ideas. Okay, so we have noisy encoder. This is encoder model parameter, decoder model parameter, and you try to learn these model parameters by minimizing this reconstruction error. So that's what it is. Denoising altogether pretty simple, right? So we already have the CNN encoder, CNN decoder. Again, this one is convolution, this one deconvolution. And then if you look at the forward from X, right? Just adding noise. Add a noise X. Noise is just a noise level is whatever the sigma is, and randomized times noise level, and return this noise. And essentially this noise, you have then you go through the encoder, you go through the decoder, then you get your reconstructed. So basically this is your forward operation for this. Okay, so basically this is denoising autoencoder. Now let's look at that example. So we have this denoising autoencoder, right? So, and we just do a little bit illustration, the similar illustration. You add a noise. You are going here, and you're going different. Seems for MNIST, it's not too hard to differentiate noise from image, because if you look at reconstruction, it's pretty similar, right? Here is more or less similar to before, so it doesn't degrade a lot. So essentially, this is the same image, basically exactly the same image from MNIST. You look at this 2-dimension and so on. So basically, the only thing is you're adding noise to that. But after that, reconstruction seems not too much different, right? So, yeah. So what is denoising autoencoder versus autoencoder? Standard autoencoder build is to reproduce its input. There is certainly large capability learn identity, or at least it's not learning enough representation. You try to just try as very hard to learn identity. And this is not good. We want to learn something more meaningful than identity. And certainly compression, like the bottleneck dimension small is good part of that. But then it may not be enough in some applications. This is why people thought about to address that using this denoising autoencoder, right? Well, for the denoising autoencoder, you add noise to the input during your training. Train the network to recover the original clean image, right? So you start with noisy input and train network to recover the original image. Force the network to extract features that's more robust to the corruption. Depends on the kind of corruption you want to put into your noise, right? You can learn different things. For example, you can shift a bit, or you can say other ways, right? So then it's robust to a different kind of corruption. But adding Gaussian noise is pretty typical, right? You can do alternative loss functions. You can also do variance, which actually used. Master language model is something very interesting that very closely related to denoising autoencoder. This one is something which is pretty important for representation learning. The first demonstration of unsupervised representation, probably through this, is this called BERT. We'll talk about that in the transformer parts. Nowadays, there's a revising interest in this, using that for generation. Yeah. And this is something we might not be able to cover, but certainly there's quite a bit of interest in this kind of models. And this one has its root in the denoising autoencoder, basically. The idea is you're masking and you're demasking. So that is one way of adding noise. Basically, noise, you just doing some corruption, and then you're getting back. Okay, so yeah. Additional regularization we will talk about next time. So not this time. So this one we will hint on the next time. We'll explain that. So next few we'll probably want to explain so why we need additional, and we will talk about generation. Here we up to now, even though we said a little bit about generation, we are focusing on representation learning, right? So mostly, but soon we will move to the generation. So we will starting in the end of this lecture, the next few slides, to hint on that and what issues we need to resolve. Then this will bring us to the VAE next time. Why we need VAE, right? Why we don't just denoising autoencoder or whatever. So let's take a look at about denoising autoencoder. We want to thinking about the generation now, okay? But now it's a representation. Let's say, because we have this dimension equals 2, remember we have this MNIST going through the denoising autoencoder to get a dimension equal to representation, right? Now let's look at what it looks like when you train. If you look at what it trains, you realize one thing, right? So there's no constraint of what Z is. I can do basically, if you look at right here, just looking this is a random Gaussian, right? This one, it's a reasonable look like that. But one thing though is you are not actually constrained, has to be random Gaussian, right? Although it just up here looks like. The other one is not a controllable Gaussian, means that your mean here, right? It's -20 around. This is probably closer to 10 to 20. It's not surrounded zero. People prefer that to be zero close. And certainly there's no control about where the mean is. You can be 10, you can be 100, because we do not make any constraint like why they should behave that way. So it tends to shift around. So it tends to, whether it should be a Gaussian, does that look like Gaussian? It's a little bit, but it's not quite, right? So basically, essentially, all I'm saying is that the embedding, what it looks like in the embedding space, we just know it's a small dimension, but we don't say what it looks like in the embedding space when you do the representation learning, when you map all these MNIST training points. This is a little bit undesirable. We want more control, especially for generation. Generation works as follows. You start with a random sample of Z. After that, you do the decoder. Once your decoder passes your generated sample, okay? Therefore, you hopefully not just random points you don't know. Your better is some Gaussian, which you know of, right? And how do you do that? This is where we say the Z space, you need regularization if you want to do the generation. And this is where we will put to the VAE to that. Essentially, okay, VAE what it does, I mean, in short, what VAE does, it makes your embedding in the Z space over your data looks like standard Gaussian. Standard Gaussian is standard deviation of is 1, and for all the directions, and then it's a zero mean, right? So it's not like this. Okay. Left is actually embedding. Right is just the Gaussian matching the mean and the covariance. Looks like they're not quite the same, right? So, but this is one thing. But certainly the mean and not quite the same. So, right. So basically, if you look at this, actually mean is this guy. Actually, covariance matrix is something like this. Okay, this is what he computed, right? So yeah. So scaling is also big, but again, you don't have control over that. You only control over the dimension. So MNIST example. So this one, if I start with z equals 0, 0, it doesn't decode anything. If I start with 32 minus 32, this one is within range of this guy with this covariance, right? This covariance is at the center here, at the covariance that one. So this is reasonable, right? So basically, yeah, we learned that. Essentially, you know, but Z is out of range. So basically, starting from 0, you say, what is the decoding? It doesn't decode anything because it's not covered by typical training data. The embedding of typical training data is not at 0. It doesn't cover 0. It covers this guy. It's a little bit cover this guy. So this one is a little bit blurred, but this one looks more normal. This is a 2-dimension, right? So, but anyway, so this is the point, right? The point is, what we want is want these to be good Gaussian approximation. The key is that there's no constraint on the embedding space, right? When you want to do generation, I show you it can be done. It's just generating random vector like this in the Z space, going through the decoder. You can generate your image. But then you want this distribution to be standard Gaussian so that I can sample from standard Gaussian, generate the image. So that's generally feasible if similar to the embedding of typical training data. That's a previous. Generally, the pool is out distribution. For example, like 0 is out of distribution, then you cannot generate well, right? Can we make embedding similar to standard Gaussian? So that's essentially the question, which is answered by VAE, which is not addressed by autoencoder, or the denoising autoencoder. Denoising autoencoder try to make it more robust. That's the thing. To less identity, but the VAE is trying to make the embedding more similar to standard Gaussian. Okay, I hope that's clear to connection about that. They are all doing representation learning, but once you do the representation learning, the side effect, you also have a generator. If you only care representation, maybe you don't need to care VAE. Although people still care about VAE because you're nice to be around 0, nice to be good shape of Z, right? So How do you do that, right? So the question is, popular solution is that, this is next topic. Next pretty heavy, but we will show some simpler solutions next time to start with just a motivation. But keep in mind, so this is what we do. We will start with a denoising autoencoder or autoencoder, but adding additional terms into your loss function so that it can behave generating something like this, right? Partial solution, we will talk about that soon next time. And here is a reference. Next time the whole lecture is on this guy, right? Require a lot of math, so that's one thing. So you have to be familiar with calculus. Okay, so that's all. Yeah, thank you. I will see you Wednesday.